Good morning, and this is for the USA EE533 lab2 demo video, and let's start it. For this demo, we use the Windows XP for the as a virtual machine. So let's power it. Okay, the whole project was finished on the settings ISE, and for the tutorial section, because of the original file was uncompiled, I use the MTV video to do the tutorial section. So let me first start it from here. Test. In the video, we use the 1-bit fighter to connect them sequentially to become a 4-bit adder. And here is the inside structure of the 1-bit adder. We get a 2 XOR and 3 AND gate and 1 3 input OR gate. So as we sequentially connect them into a 4-bit adder, we can get a 4-bit full adder. So let's then do the simulation. In the simulation, we don't have the waveform file, so we need to manually input all the inputs. So let's run for a while, and now give the A 0 0 0 0 and give B 0 0 0 and the C in 0. So we expect to have the C out and the S to be 0, and it's good. So then we can change the input to 0 0 1 and B to 0 0 0 1 and C, which we keep it to be 0. So we run it. We expect to have 2 here. So it's 2. That's great. So we change it to the 0 1 0 0 and the 0 B to 0 1 0 0 0 1 0. So the 4 plus 2 is a 6. So we run it. Also, it's 6. And that's it. That's all for the tutorial section. Let's close it. Okay, for the next part is the synchronous AB adder. In synchronous AB adder, we need to have AB adder and make it to be a sequential logic. So first, for the AB adder is here, we connect 8 1-bit full adder sequentially and make it output to the next input. So make it to be a AB adder. To make it sequentially, we have the flip-flop in front of the input and the output. So to do the simulation for it, we have the waveform file. So we don't need to input this inputs data manually. We can study it and do the next thing only to do is the simulate. Click the button, and now we can see the waveform, and we run it for the 4,000 nanoseconds because we already run for 1,000 nanoseconds and we need to click it. So we already run the 5,000 nanosecond to see the full waveform. And we can see this is 13, 12 to make it a 25, 0, 1, 13 to make it a 14, 0, 1, 0, 1, 2. And we have the enable signal here. Oh no, it is clear signal here to clear it. And now clear goes down and just do this add 1 to 1 is a 2. So it's good. The next part is to make the 8-bit full adder to become a 32-bit adder. So for this part, we have this one. Okay, we got a 32-bit adder in the center of this schematic, and we also have the D flip-flop in front of the inputs and after the output. So let's do the simulation here. Okay, we can see the simulation looks good. We have 1 1 at the beginning, and we change the setting to the 1 as at next the post edge of the clock. We become to see the 3 here, so it's good. And the third part of this lab is to make a 32-bit adder to become extended ALU, which means it has to have another function like the AND gate OR gate for the each bit of the data, and also the shift to the left or the shift to the right, and sub function. And now let me show you this one. Okay. Okay. This is so without the flip flop in front of the input, and without the flip flop outside the output, we can say you do this module with a add and sub module, the AND module, and OR module, and the shift left module. I connect them with a MUX 32-bit MUX 5 to 1, and use the opcode. For the opcode 000 and 001, I connected both to the one port to the AND and the sub module, so that when the opcode is 1 and is 0, it all selects this module. But for the sub selector, I connect to the opcode 0 bit. So when the 0 bit is 0, it does the add function. When the 0 bit is 1, it does a sub function. So it's all makes sense. And at the top of it, I connect this module, which called the ALU module, have the D flip-flop like the previous part, the 8-bit adder and the 32-bit adders. We all have this kind of the D flip-flop, so I uh don't do other things. So I just connect them and connect every input of it, and connect the clear, the clock, and also the enable signal of the algorithm. So next we run the test fail. Okay. This is the setting of the test fail, and we do the simulation. Okay. And run for certain. We will. Okay. And for the opcode 0, we have the add function. So as the 0 plus 0 is 0, and the 0 plus 000D, which is 12, it should be 12. And it's hidden here, but it's a 12. Uh, Maybe I can make it to be unsigned. Sorry, it's a 25. That's my fault. Okay, it's a 12 plus 13 is a 25. That's good. That's correct. And then we have the output to be the 28. That's because we change the input from the 12 to the 15, and we have 28. And then we have opcode the 1, which means to make it a 15 minus 13 to be 2. And then we have opcode 2, which is the end. So the end here is A and the A. And it should be the A. Yeah. And then we have opcode 3, which means A should, or the 55555, which means 1 1 1 1 1 0 1 0, or 0 1 0 1. So it should be 1 1 1 1 at the every bit of this hex data. So it's a 5 F. And at the end of the simulation, we change opcode to the 4. The 4 is, which means the 1 0 0 have this opcode. We can change the input data A to make it every bit to shift left 1 bit. So it become the 555555554. And that is all for this project. And also there is another version of this ALU. We use the Verilog for it, and let me just show it. So it's ALU new. So in this project, I only use a Verilog without schematic. So I write a test bench for it, and there should also have a Verilog version. Yeah, in the Verilog version, we do all these implementations, use Verilog. So there's no schematic. Okay. So again, do the simulation. No, I don't want to close it. Okay, let's have a look. Okay, so the same thing in the output 0, it should be 5 plus 10 is 15. 1 plus, okay, when is the output 1, it should be 10 minus 5 to be 5. And also when its opcode is 2, it should be the OR. And 3, when opcode is 2, sorry. When the opcode is 2, it should be the AND logic. And 3 is the OR logic. And when it's 4, it should be shift to the left. And when it's back to 0, it becomes to the AND logic. So that's all for the EE533 lab2. Thank you for watching.